What does convergence mean? Just smaller? What's that? Yeah, it approaches a certain point, which we can call a limit. What is this dealing with? What operations are we dealing with? Integrals, derivatives, what? Have we done any integration so far? Oh, we just been dealing with series and sequences. Sequences and series, because we haven't talked about areas in a long time. So what we're looking at here is absolute convergence of sequences or series. In other words, for example, if a function is increasing, it diverges. If it's decreasing, it's convergent because it's approaching a specific number. This way it's going to infinity. This one's going down to 0. What about when terms alternate in sequence? What if we had that? What does monotonic mean? It's either increasing or decreasing. So it's non-increasing or non-decreasing, which means just the opposite. So is this non-increasing or non-decreasing? No, it can't be and. It's either non-increasing or non-decreasing. It's monotonic means it's one of the other. This one, on the other hand, has n. If n is even, what happens to this number? Positive one for n even. If n is odd, so it alternates between two terms. When it does that, we don't know for sure whether it converges or diverges. We're not sure. We have to do some other tests. For example, the example that they use here is look at the first few terms of that sequence or that series. So what's the first term? What? Okay, what's the next term? Let's look at the first time. If n is 0, this comes into 1, so it's 5. It's a summation, so we plus. Now we have 5 times negative 1/4 to the power 1, which makes this negative 5/4. Then we have negative 1/4 when n equals 2. That equals 5 positive 1/16, which makes it 5/16. When n is 3, the top is going to stay negative. Now it's 4 to the third power is 64. So we have negative 5/64. And you notice it's always going to change, it's alternating signs. Have we seen anything like this before? We have seen this before. Last couple of sections. If we have that, how can we simplify it? What does it become? We could summarize it into that. So the question is, depending on what R is. if we look at the absolute value of R and it's less than 1, what do we know about it? If R is less than 1, what happens to it? Whereas if this fraction is a proper fraction, which means as n goes larger and larger and larger, what happens to this equation? You can answer 0, so converges. If the absolute value of R is greater than 1, what happens? In other words, if R, this is a proper fraction, which means it's less than 1. If it's an improper fraction, it means it's greater than 1. What happens to the function there? Because it's greater than 1, it keeps on getting bigger and bigger and bigger, so it diverges. So now we'll look at this definition. A series A sub n, summation of A sub n, converges absolutely if this corresponding series of absolute values converges. In other words, if it's alternating, well, let's look at what happens when we take the absolute value of it. Is it heading to a value or is it not heading to a value? That's where we say converges. It converges absolutely, or it's absolutely convergent. You use either of those terms. Or we say it's absolutely convergent. Because we're taking the summation of the absolute values of our sequence, of our series, I mean. So now this is a true statement. An absolutely convergent series is convergent. But now how about, can we say the other thing? An absolute is convergent. Is a convergent series absolutely convergent? Can we say that? What does it mean to be convergent in the first place? It goes to a specific point. So now, if I take the absolute value of the series, will it change where it's approaching? It shouldn't. No, it shouldn't, because think about it. If it's getting smaller, 1 over n, if it's getting smaller, 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 if I take the absolute value, it's still going to get smaller, smaller. It's just going to be positive this time. So yes, it is true. So here's theorem 12. The absolute convergence test. If the summation of, as n goes to 1 to infinity, of absolute value of A sub n, if it converges, then the sequence converges. So if the summation of the absolute value converges, then so does the series itself. That's what it means to be absolutely convergent. Let's look at an example here. A. As n goes to 1 to infinity of -1 n plus 1. It says in the direct instructions, this example gives two series that converge absolutely. So what this looks like, let me see, times 1 over n squared. It's got to be alternating sequence. Remember what the last section said. When we take our summation, in order for us to be able to use these rules, do we always have to start at n? At 1? Because if you notice, this one goes to n plus 1. If we go from 1, we have to go to n plus 1. If we start at 0, then we would go to n. And it still goes to infinity. But if we start at 1, we have to go one more than the n value. If we start at 0, then we go to the n value. So let's look at these sequences. When n is 0, when n is 1, 1 plus 1 is 2, so that's positive. So we have 1 over 1, that's 1, that's 1. When n is 2, this is n is 1. When n is 2, so we have 3, so it makes it -1. N equals 2. So we have 1 minus 1/4. N equals 3. 3 plus 1 is 4. 1 over 3 squared makes it a positive 1. So it's 1 over 9. So -1 to the 5th makes it -1. One over 5 squared, which is 1 over 25. So it's -1 over 25. So it alternates sequences. So what do we know about this? Is this value going to converge or diverge? Oh, 16, yes, I'm sorry, it's 4. So it's supposed to be 16, yeah. But n is 4. So what's happening to the sequence? Is it converging or diverging? Look at the numbers. If we looked at this in a graph, when n is 1, it's 1. When n is 2, it's -1/4. When n is 3, it's positive 1/9. When n is 4, so what's happening is the sequence is doing that. It's what's called dampening. So this converges. Now, does it converge absolutely? In other words, if we took the absolute value of it, So we look at our sequence. Since we're taking the absolute value of it, we don't need this first part. Because if we take the absolute value, all this thing does is make it positive or negative. That's all it does. So all we really have is the absolute value of 1 over n squared. Well, this can never be negative to begin with. So we really have 1 over n squared. As n gets bigger and bigger and bigger, this thing converges. So it converges absolutely. Let's look at B. How about this sequence, or this series? N equals 1 to infinity of sine n of over n squared. Does this one alternate signs? Why? When n is 1, when n is 2, when n is 3, when n is 4. So we have sine 1 of 1, sine 2 of 2 squared, which is 4, sine 3 squared is 9, sine 4 over 16, and so on and so forth. Does it alternate signs? What are the values of sine? What is the lowest and what's the highest value of sine? -1 to 1. So yes, these alternate signs, depending on where these angles or these values stay. Since what's happening here, we have sine n 1 over n squared. Since the numerator can only be plus or minus 1 or 0, then it might be only 0, it doesn't matter. What's happening to the bottom numbers? They're getting bigger. Does this sequence converge or diverge? Because the value is getting smaller and smaller and smaller and smaller and smaller as it goes along. So if I take the absolute value of sine n, what's happening here is now each of these values will remain positive. So since the absolute value of sine n, it can't be negative anymore. It's either going to be 1 or 0. That means the number is going to start decreasing. So it converges absolutely. The ratio test. The ratio test measures Remember, whenever we deal with a fraction, like the slope y over x, we deal with a rate of something. Measures the rate of growth. There's always going to be growth? No, because it can be positive or negative, or declination of a series. We do this by examining the ratio of a n plus 1 over a sub n. What does a sub 1, n plus 1 over a sub n, what does that mean? Have we seen that before? When? Where? You can't just say yes, you have to tell me where. When is that system used? It's used in a geometric series. Geometric series have a common ratio. Arithmetic series have a common difference between each number, which would take the second number minus the first, third number minus the second, fourth number minus the first. The differences are always the same. The geometric series has a common ratio. So if we have our numbers A1, A2, A3, A4, A5, between any two numbers, A2 over A1, A3 over A2, A4 over A3, A5 over A4, all of these ratios have to be the same. A common ratio. Only works for geometric series. So now, if we had a rate of growth, we could also look at it this way. R n plus 1 over a r to the power n. What does that equal? Because if each one of these are the same, what does it equal? It equals some number r. Is the common ratio r. The a's cancel. All we have left with is r. Why is that? R1, R2, R3, R4, R5. R0, R1, R2, R3, R4. Because remember, the top has to be bigger than the bottom. So what happens here, the R0, the initial R is 0, then these cancel, these cancel, these cancel, these cancel. So all we're left with is R to the 5th, which is the Rn plus 1th. It's the actual location of that one. Theorem 13. The ratio test. Let the summation of a sub n be any series, whatsoever. And suppose that the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is equal to some value p. Then a the series converges absolutely if p is less than 1, which we just proved that. The series diverges if what? P is greater than 1. Or P is infinite. And the last one, if P equals 1, can't use it. Can't use the test. So basically, what does this tell us? If we have a proper fraction, which is the top is smaller than the bottom, then the P will be less than 1, which means it converges. It gets smaller, smaller, smaller. If it's an improper fraction, the top is bigger than the bottom, it gets bigger and bigger and bigger. That's what it's telling us. So let's look at an example. Example 2. Okay, investigate the convergence of the following series. A summation as n starts at 0 and goes to infinity. Since it starts at 0, my n's are just n, not n plus 1. If investigate the convergence of the series. So does it converge or does it diverge? How do we know? What can we do? We can rewrite this equation since we have a monomial on the bottom. Hold it, let me see. Hold it. No. What I have to do first is I have to see how this behaves. So how do I write this? This is the a sub n. How would I do the a sub n plus 1? That's a sub n over 2 to the power n plus 5 over 3 to the power n. I took this first. So how do I simplify that? I have 2n+1 + 5 over 3n+1 times the flip of the bottom. Let's get the threes together. So we have 3n over 3n+1. Then we have the 2n+1 + 5 over 2n+5. So what happens to the threes? If I cancel the first n threes, how many more do I have where? I have one more on the bottom because I cancel out n of them. Now, what do I do here? So I have 2n+1 + 5 over 2n+5. When we looked at asymptotes, horizontal asymptotes, whenever we had an equation like this, what we did was we divided each term by a value to get, because we can't get rid of the top. If we get rid of the top, and we get too many on the bottom. So if we multiply each term by 2 to the power -n. Okay, now why is that? What is 2 to the power -n? It's 1 over 2n. In other words, I'm dividing each of these terms by that coefficient. And you'll see why we're doing this in a second. So we have 2n+1 over 2n plus 5 over 2n, 2n over 2n, 5 over 2n. So now what happens here? What goes on here? I have 2n to the power n+1 over 2n. I can cancel 2n, which just leaves me 2 on top. Plus 5 over 2n. The 2n and the 2n cancel, leaves 1. As n gets larger, what happens to these? They go to 0. So what we're left with is 1/3 times 2, which is 2/3. So it converges. Because yeah, you said it correctly. It's pretty much just we do this because we can take the limit of it. It approaches a limit. Let's look at B. B says. Hold it. I should notice this. Let's look at A again. Another way we could have done it. What's that? Remember, when I started off originally, the way I was going to do it. Since the monomial on the bottom, so that's the same as in this one, it's 2 over 3 to the power n. It goes from n equals 0 to infinity, plus the summation of 5 over 3 to the power n. So what does that equal? If we expanded these, what do we get? Remember, remember when we had this, we can write it as that. If we get it into the rate of change and the repeating term, we can rewrite it this way. So in this first example, in this first term, what is A? A is 1. R is 2/3. How about in the second one? So we get 5 times 1 over 3 to the power n, which becomes 5 times 1 over 3 n. Remember, R has a power n. So that's my A and that's my R. So rewriting this one, I have, remember, I'm using the A over 1 plus R. A is 1, 1 minus 2/3, plus A is 5, 1 minus 1/3. One is the same thing as 3 over 3. 3 over 3 minus 2 over 3 is 1 over 3. 3 over 3 minus 1 over 3 is 2 over 3. Flip the bottom, so we have 3 over 1. 3 over 2 times 5 over 1. 3 over 1 plus 15 over 2. I'll use the butterfly. 3 times 2 is 6. Plus 1 times 5 is 1 times 15 is 15. So it equals 21 over 2. Now, that's not the limit. All this tells me is that P is greater than 1. So what does that tell me? No. What's my P? Because remember, we have to look for a couple of things. Which one of these conditions does it fall into? Remember what P was defined as? P is the limit of A sub n to that. That's my value P. So when I had this, this is my P. That's less than 1. If it's less than 1, it converges. It converges to that value. Look at B. B says the summation of n equals 1 to infinity of 2n factorial over n factorial n factorial. We're looking at the ratio test here. The ratio test is looking at this. Now, the ratio test only works for a couple of conditions. You have to either start at 0 or 1. So, since we start at 1, we can use the ratio test here. So what does this equal? What would a n plus 1 look like? Because we need to do a n also. A n sub 1 why is it 2n plus 2? Because if I made n plus 1, then it's 2n plus 2. That's 2n plus 2. What happens to the bottom here? N plus 1 factorial, n plus 1 factorial. That's the top. Because I add 1 to each n. On the bottom, it is what it is. So it's 2n factorial, n factorial, n factorial. Take the top, leave it alone. 2n plus 2 factorial, n plus 1 factorial, n plus 1 factorial. Flip the bottom. N factorial, 2n factorial. All right. So can anything cancel? Look at the 2n plus 2. The 2n plus 2 means this. 2n plus 2 times 2n plus 1 times 2n all the way down. So now then it's factorial. N factorial, n factorial. N plus 1 factorial means n plus 1 times n factorial. Same thing with that one. N plus 1 times n factorial over 2n factorial. I just stretched them out because now I can see what's in common and cancel them. The n factorials can cancel. The 2n factorial can cancel. So that gives me 2n plus 2, 2n plus 1 over n plus 1, n plus 1. Can anything cancel? Look at this first term. I can factor out a 2. So the n plus 1 can cancel. So that's 4n plus 1 over n plus 1. What do I do next? Divide each term by what? N. Because it's the same as finding the horizontal asymptotes. So the n's cancel there. So we have 4 over 1 plus 1 over n plus 1 over n. As the limit of n goes to infinity, so my, yes. Oh, yeah, yeah. But it's still gonna go to 0 because it's a constant, so it's gonna go to 0. But yeah, good catch. So what does this tell us? Remember what that was, since this is my p-value. Since p is greater than 1, it diverges. Remember, the ratio test doesn't find the limit, it just finds me the p-value. That's what I said here, the limit as n goes to infinity. That's why these disappeared. Right here. The ratio test, once we do this, we take the limit and that gives us our p-value. If the p-value is less than 1, it converges. If it's greater than 1, it diverges. If it's equal to 1, we can't do anything about it. Let's look at C. The summation as n goes from 1 to infinity of 4 to the power n, n factorial, 2n factorial. Remember what we have to, this is what we're looking for here. And that's, instead of a limit, it's going to give us a p-value. That's what we're looking for. That's the ratio test. So we have 4 n plus 1, n plus 1 factorial, n plus 1 factorial over 2 n plus 1 factorial. That's the top part. Divided by 4n, n factorial over 2n factorial. So this one here will be 2n plus 2 factorial, 4n plus 1, n plus 1 factorial, n plus 1 factorial. Flip the bottom, so we have 2n factorial and 4n n factorial n factorial. So the 4n's. The 4n and the 4n cancels out, leaving me with what? Just a 4, with 1 4. So that and that cancel, leaving me a 4. N factorial, n plus 1. Will leave me an n plus 1. Because remember, the n plus 1 factorial is n plus 1 times n and everything else below there. Times n minus 1 times n minus 2. So since we start with n plus 1, everything after that is n factorial. Same thing. So both of these cancel with those, leaving me with n plus 1, n plus 1. The 2n and the 2n plus 2, so it's 2n plus 2 and then 2n plus 1 on the bottom. So everybody see what's happening there. What happens here? Because what 2n plus 2 tells us, it starts off at 2n plus 2 times, what's the next one below it? 2n plus 1. What's the next one below that? 2n. Then 2n minus 1. So here, the 2n's can cancel. We're leaving us with what the coefficients are. So this one cancel here. I have a 4 n plus 1, n plus 1. Here I can factor out a 2. So the n plus 1's cancel. The 4 and the 2 cancel, so I have 2 n plus 1 over 2n plus 1. Two n plus 2 over 2n plus 1. What do I do next? I divide each term by n. So 2n over n, 2 over n, 2n over n plus 1 over n. Two plus 2 over n, 2 plus 1 over n. Take the limit as n goes to infinity. That goes to 0, that goes to 0, that goes to 1. So the P equals 1, there's nothing we can say about it. The root ratio test cannot be used here. So what can we say about this ratio? All this tells us is the ratio test can't be used. But do we notice anything else about the sequence? What do we notice about this? Because that's our summation. Does it get bigger or does it get smaller on top than the bottom? Well, yeah, the top's always going to be bigger than the bottom. So since the top is bigger than the bottom, it diverges. Because an plus 1 is bigger than an. It's an improper fraction for each term. Don't believe me? Plug in the values. 4 to the power 1 is 4 times 1 times 1. 2 to the power 1, 2 times 1. 4 divided by 2 is 2. Now when n is 2, that's 16 times 2 times 2. There's 64. 64 over 4. So 64 over 4 times 3 times 2 times 1, which is factorial. So 4 goes into 64 16 times. So we have 8 over 3. Is 8 over 3 bigger than or less than 2? Bigger than. Because when n equals 1, we had 2. When n equals 2, we had 8 over 3, which is bigger. So it's getting bigger each time. So that's why it diverges. Now what about the root test? This test is used whenever our sequences are not so straightforward. Because up until now, we have the convergence tests we did in the past, but now when we have something like this, where it's conditional, then we have to use something else. So to do that, we have to look at each term of our sequence. When n equals 1, when n equals 2, when n equals 3, when n equals 4, and when n equals 5. So when n is odd, when n is 1, we use this top one. So it's 1 over 2 to the first. When n is even, we use the bottom one, 1 over 2 squared. 3 over 2 cubed. Oop, no, this is, yeah, it's 1 over. When n is even, I use 1 over 2 to the fourth. When n is odd, I use this one, 5 over 2 to the fifth. So you look at the sequences. 1/2 plus 1/4, 3/8, 1/16, 5/32. Is it an arithmetic sequence? No, because if we subtract each of these individually, we won't get the same difference. So it's not arithmetic. Is it geometric? Does it have the same ratio? No. because 1/4 divided by 1/2 is 2. But 3/8 divided by 1/4 is not 2. So it's not geometric or it's not arithmetic. So what do we got to do? So we have to look at what we have so far. We look at the ratio test produces this. If n is odd versus n is even. So we have 1/2n. This is n plus 1/2. So this is what we're going to be using as n goes to infinity. The root test. Let the summation of a sub n be any series. And suppose that the limit as n goes to infinity of n to the absolute value of a sub n equals p. If p is less than 1, it converges. If p is greater than 1, or p is infinite, it diverges. B and C. If p is equal to 1, it's inconclusive. We have time for this. Have we seen these conditions before? The last test. So all we have to do here is this: take the limit, take the nth root of the absolute value, and see what happens. So let's take an example here. Consider the term a sub n, the one we just had. n/2n and 1/2n. Does the summation of a sub n converge? Again, what would mean that it's converging if we're using the ratio test? If p is less than 1. So let's set it up. We look at summation of the absolute value of a sub n. So anywhere we see an n, put an nth root around it. This is for n is odd. This one is 1/2 for n is even. Because why is it 1/2? Because if we took this number here, let's look at the bottom numbers. Let's see what happened here. A sub n is equal to n/2n, right? Take the absolute value of it. take the nth root of it. It's a quotient, so I could take the nth root of n and the nth root of 2 to the power n. Nth root of 2 to the n, what happens there? The n's cancel. So we have 2 on the bottom. Why don't we need the absolute value sign anymore? Because n is from 1 to infinity, or 0, so n can never be negative. So that's why this one becomes that. Let's look at the second one. A sub n equals 1 over 2n. If we take the nth root of both sides, nth root of 1, nth root of 2 to the power n. Nth root of 1 is 1. The root and the exponent cancel, so we get 1/2. That's why we went from here to here when we took the absolute value, the nth root of it. So what do we know about these two? We're looking at bounds. Which one's bigger? Is 1/2 or nth root of n over 2? Which one's bigger? Because what we're comparing to it is the nth root of the absolute value of our sequence. It has to be between there. So is the nth root of n bigger than 1? Ever bigger than 1? Yes. So our sequence has got to be within there. Since it's bounded, what do we know about the summation of a sub n? Does it converge or diverge? Because it's within a bound. It's finite. We could even look at the sandwich theorem. So remember we had 2 bounds. The worst this one can become is 1. So if it's 1/2, 1/2, this one goes to 1/2. So it's bounded. It's absolutely convergent. All right. Example 4. Which of the following series converges and which diverges? Let's go down these. Summation n equals 1 to infinity of 2n n cubed and c. One plus n. So which ones converge, which ones diverge? So what test do we do for these? Remember, what did the root test tell us to do? So we take the nth root of everything. See what happens. So the nth root of n squared over 2n becomes the nth root of n squared over the nth root of 2n. On the bottom, the root and the exponent, so it's just 2. And on the top, we have the nth root of n squared. We can take out that square term. As n goes to infinity, what does this become? So what happens here? As n goes to infinity, the limit, we get this. Since 1/2 is less than 1, it converges. So let's look at the second one. So we have the nth root of 2n over n cubed is equal to the nth root of 2n divided by the nth root of n cubed. The nth root and the 2 to the power n becomes 2. And on the bottom, we have cubed. What, as n goes to infinity, what happens to the nth root of n? It goes to 1. Since 2 is greater than 1, it diverges. And the last one, we have the nth root of 1 minus 1 plus n to the power n. The n's root and the n exponent cancel out, so we have 1 over 1 plus n. As n goes to infinity, what happens here? Where does it go to? Since 0 is less than 1, it converges. Oh, we'll do the last one on Thursday. Because I have to go somewhere by noon. Or it's a pretty short one. I mean, I could send you the video of it. What's that? Or yeah, we could have lecture online Thursday. So we'll do lecture online. Also, I forgot. Yes, we'll do that. Oop.